we talked about how if you have a short exact sequence of complexes, then you get a long exact sequence in homology. So the maps of complexes induce maps on the homology groups, and then we built, by having fun with diagrams, a connecting homomorphism that fills in the sequence, connects the sequence to make it exact. Great, and so then we applied this to a pair to get a long exact sequence and to a triple. Right, and this will happen over and over. Every time we have a short exact sequence, we get a long exact sequence. So the short exact sequence corresponding to the pair, or to the augmented short exact sequence corresponding to a pair, and you get a long exact sequence in homology. Recall here that the convention is that if A is not empty, then the reduced relative homology group is the same as the unreduced relative homology group. And if A is empty, then the convention is this just Hn of x. We also saw, for example, that the reduced homology of a space is the relative homology of x with respect to any point. Right? So we could have just introduced reduced homology as relative homology groups. In some ways, it's better to have done it the way we did, in that there's no choice. Whereas here, of course, you choose a point. It doesn't matter which point, it turns out, but there is a choice. OK, so we saw some immediate consequences having these long exact sequences. And then we talked at the end about excision. So excision says that when you're looking at relative homology, you can excise a subset of A as long as the closure of Z sits inside the interior of A. So the proof, which we'll go over in a moment, takes a little bit of work, but the main idea of the proof is pretty simple. So to give the main idea, we talked about what happens for delta complexes. So we said, e.g., if X has a delta complex structure, with A x minus z and A minus z as subcomplexes, then all you need to do is look at the map from x minus z into x to the relative xa. So the composition here, phi, we saw that that phi is surjective, and the kernel of phi is just the n simplices that are in A minus z, and so it induces an equivalence of simplices, this mod out by delta, not simplices, the equivalence of chain complexes, chain complex groups, this n delta n x a. Okay, so this works out great in this case, as long as you have a delta complex structure that has each of these as subcomplexes. So the problem in general is that you don't have this nice decomposition of your simplices, right? If I give you an n simplex, a singular n simplex in X, you don't get to write it as something that lives in X minus z and something that lives in A, right? You don't get to decompose it into pieces like this automatically, right? Whereas in this case, we're just saying, well, if you can, then here's the proof. Okay? So what we want to do in general is make this proof work. So in general, for singular simplices, we can, let's say, essentially make this proof work. But we need to subdivide a singular simplex into pieces, each one in either in A or in X minus z. Right? This gives us a cover of X, right? And in fact, the interiors cover X by that condition. And so, and a simplex is, I feel like it's compact. So we'll be able to cut it into small enough pieces so that each of the pieces maps into the interior of one of these sets. Right? And then we'll be able to run this proof. Yes?
Before we do that, I feel like I'm still pretty confused about what, for example, in the delta complex example, delta n of x comma a would be. I feel good about delta n of a single set. But when I have the space in its subspace.
Yes. So the definition would be delta n of x mod delta n of a.
Okay.
Right? So that's the definition. But in some sense, it's much simpler here. Because remember, when you have a delta complex structure, then you have, let's say that it's a finite delta complex structure. So you just have finitely many simplices that make up your space. Right? So, and we're saying that A has a sub-delta complex structure. So we have a basis of elements making up delta n of x. And in this basis, we have some that are entirely in A, right? And some that stay in X minus Z, for example, and some that stay in A minus Z. But so over here, all you're doing is you're saying, okay, everything that maps into A, ignore it, right? But you have basis elements. Your basis elements are maps into A and maps that don't go into A. So all you're doing is look at the basis elements and look at everything that mapped into A and ignore those. So you're just deleting elements of your basis. Sure. Okay. Okay, so this is the idea. This is what we want to do. We're going to subdivide simplices until they map into one of these elements of the cover, right? So there's nothing special about having two elements of the cover. We could have any amount of elements in our cover. So let's set it up like that. So given X a topological space and a cover, say use of alpha with X equal to the union of the interiors. All right, so I'm not going to assume that they're open, just that the interiors cover. And I'm not assuming that it's finite or that this is compact. Okay. Let C and U alpha of X. This is going to be, so remember that the nth chain group of X is just all of the singular simplices mapping, is the free abelian group on all of the singular simplices mapping into X. So now we're going to take the free abelian group on all of the singular simplices whose image lies in the interior of one of these guys. Right? So free abelian group on all singular simplices. Such that the image is inside U alpha interior for some alpha. Right? So it's a subgroup. It's a subgroup of this one because I'm just restricting some of the basis elements. I'm just taking a subbasis of the free abelian group. And this condition is preserved by the boundary map. So the boundary map restricts to these subgroups, and so we have a subcomplex. Okay. So the proposition is that the inclusion of this complex induces an isomorphism between the cohomologies. Right. And we're going to denote this group by HN U alpha. Okay. So proof is going to be by subdivision, right? But the tricky thing, is that, so we're going to give some algorithmic way of subdividing a simplex, but how many times you have to do the subdivision before the images of the subsimplices sit inside the cover depends on the simplex. Right? So we're not going to be able to do it all at once. Rather, we're going to come up with some subdivision operators, and then for each simplex, we can apply some number of these operators, iterate some number of times until we get something that works. Okay. So for each x, we'll construct a chain map S for subdivision from chains of x to chains of x, and a chain homotopy map from, well, let's see, chains n to chains n plus 1, such that so it's going to be a chain homotopy between the identity and S. Right. So remember, a chain homotopy, this just means a group homomorphism between these groups. And what makes it a chain homotopy is that when you pre- and post-compose with the boundary, then you end up with something, and that something is automatically trivial on homology. Right? So the existence of such a T says that S and the identity induce the same map on homology. Which is good, right? When we subdivide a simplex, we don't want that changing the homology class. Okay, and we're going to ask that for any map between spaces. So we're going to do this construction. We're going to construct these guys for every x. And then we want it to not depend too much on x. So we want it to be natural in x is the phrase. So what that means is that anytime you have a map, we're going to have the induced map intertwine the two copies of S and the two copies of T. Right. So it doesn't matter if you subdivide and then map to X or subdivide when you're mapping into Y. Right. This map will take them one way of doing it to the other way of doing it. Okay. And for any cover, U alpha of x and any simplex, any singular simplex, there exists an M such that Sm sigma is in C of x. Okay, so if you give me any simplex, then subdividing that enough times, I end up with something where each subsimplex maps into the interior of one of these open sets, one of these sets. Okay, so that's what we're going to do. It will follow okay, well, first of all, that although these are defined on arbitrary chains, they restrict to the chains associated to the cover. S and T restrict. And if you take Tm equal to T and then put 1, so the identity plus S plus up to S to the m minus 1, this will satisfy boundary T plus T boundary is equal to identity minus Sm.
When you say it will follow, you will show explicitly that it will follow, or is that
Yeah, so, this one should be clear, and this one will be clear if I write, let's do the case m equals 2. So e.g., if t2 is equal to t plus ts. So if you do boundary t2 plus t2 boundary, then this is boundary of t plus ts plus t plus ts boundary. So that's boundary t plus t boundary plus boundary ts plus ts boundary. Now, by assumption, this is identity minus s. And also by assumption, S commutes with the boundary map. So I can move this S over there, and this becomes identity minus S times S. Right? And so I have identity minus S plus S minus S squared. So I have identity minus S squared. And the general case is the same, just more dots. Okay, so the key thing is, how do we construct these guys? Well, actually, before we do that, let's check that if we can do this, then we can prove the proposition. Okay? So once we have these S and T, we have the proposition. So here, let's call this inclusion I. So let's check that Hn of I is an isomorphism. Let's check that it is, say, surjective. Okay, so you give me a homology class, an Hn of x, so it's represented by C in Cn of x with boundary of C equal to 0. Right? By assumption, there exists an M such that Sm of C is actually a chain in U alpha, in the chains corresponding to U alpha. So I need to know that this represents this class. So I apply, so we know that boundary Tm, did I put the m on the bottom, plus Tm boundary of C is equal to C minus SMC. But I also know that C is a cycle, so this term dies. So that tells us that the class of S, M, C I guess I should have pointed out. So and boundary of S to the MC is equal to S to the M boundary C is equal to 0. So it does define, it is a cycle. This does define a class in here of X. And if you look at the map induced by inclusion, then this is equal to, so now I'm just looking at the class in here in this chain, right? I can write SMC as SMC plus boundary TMC, and that's equal to the class of C. Right? So this map is surjective. Right? And let's check that it is injective. So assume that you have a class in Hn U alpha of X such that, right, so this is represented by a chain in here with boundary of C is equal to 0, and assume that Hni of C is equal to 0 in Hnx. So that's the same as saying that there exists a B in Cn plus 1 of X such that C is equal to the boundary of B. Right? I want to show that actually the class you started with was 0. Right? So I want to show that there is some chain corresponding to the cover that whose boundary is equal to C. So again, there exists some M such that SMB is in is a chain corresponding to the cover and right, and I also know that okay, so let's just hit this with the chain homotopy and see what we get. Right? So if we hit SMB with this, then the boundary. Oh, hold on. What's what I'm supposed to do? Yes, this is what I'm supposed to do. Plus TMB. So let's just skip that and say what the answer is. So let B prime be SMB plus TMC. Right, so this is in Cn plus 1 U alpha X. And let's just hit this with the boundary. So boundary of B prime is equal to boundary of SMB plus boundary of TMC. Boundary commutes with S, so this is just Sm of the boundary of B, and boundary of B is C. So this is just SMC. And then boundary Tm of C, well, boundary Tm is equal to C minus SMC plus or minus Tm boundary C. Right? But boundary of C is 0, because C is a cycle. And then SMC cancels with SMC, and we end up with just C. Right? So the class of C is equal to 0 in H and X corresponding to the cover. Okay, so the proposition is proved if we can construct S and T with these properties. Okay, well, so first assume, so now we construct S and T. So first assume that X is a convex subset of some Euclidean space. Okay, because I want to be able to talk about linear functions and take cones and things like that. So let's assume we're working here, and then we'll figure out how to transfer this to an arbitrary topological space later. Okay, so assume we're working there. And let's define a coning operator as follows. So for each P and X, and simplex, so I'm going to use Q, although I'm coning because C is already doing too much work. So Q will work for cone. So the cone on sigma with vertex P is going to be it's going to be a map from the n+1 simplex to X. And so what it does to a point T0 to Tn+1. So remember, the standard n+1 simplex is just all n+2 vectors with non-negative entries that add up to 1. Right? So okay, take such a thing, and I'm going to tell you what point in X to take. So take T0 times P, and then takes 1 minus T0 times sigma of, and then take the other entries and just divide them by 1 minus T0 until you get to Tn+1 divided by 1 minus T0. As long as 1 minus T0 is not 0, right? If it is 0, then just take P, right? So P if T0 is 0, just 1. Okay, so notice that because we divided by that, they add up to 1, so sigma is defined there. And so all we're doing is taking whatever sigma was doing, and we're coning it off. Coning it off with the point P, which is already in X. Right? So this is why we need to be working a convex subset of Rn, because I need to be able to add points.
What does the term coning mean?
Oh.
Other than, like, is that just, this is the definition of coning?
You can take this as a definition, but if sigma is doing this, then I'm just taking a point P and
Okay.
yeah, taking that as a vertex and just attaching it to all the vertices that you had before.
Okay.
So yeah, it's geometrically coning. Okay, so of course we want to know what happens when you hit things with the boundary. Let's see, do I want to put the boundary? Yeah. Well, okay, before I can make sense of things, I should say, and extend linearly. To a map. QP from chains, singular chains degree n to singular chains degree n plus 1. All right, so this is what you do to each basis element, and then you extend linearly. Okay, so now an easy computation shows that when you take the boundary, you get sigma minus QP of the boundary of C if n is positive, and what you get if sigma is a simplex of degree 0 is sigma minus the augmentation map of sigma times p if n is equal to 0.
What is C?
C is sigma.
Oh,
Sorry.
right.
Yes. Yes, so the boundary map gives you, so let's look at this guy. So you have sigma, which is this one, and then we've taken the cone over that. So what is the boundary of this? Well, this says it's sigma, so that face, the bottom face, and, let's not worry about the sign, and the cone over the boundary of sigma, right? So take the boundary of sigma and cone that. So you get this cone, you get that cone, and you get that cone. So we're getting all of the faces of the pyramid, right? All the faces of the pyramid are either the cone over a face of sigma, or it's sigma itself is one of the faces, right? And you just do the algebra to see what the signs are. So in particular, this does give us boundary QP plus QP boundary is equal to the identity. You know, for the augmented complex, something similar in degree 0. So that tells us that the homology of X is identically 0, because it says that the identity map induces the trivial map in homology. But of course, we already knew that because X is a convex subset of Rn, so it's contractible, right? So that's a tilde. So we already knew this, but you know, this would be another proof. Okay, well, because we're in Rn and we can talk about linear combinations, we're going to restrict to simplices that are linear. So we'll say that a singular n simplex is linear if it's linear. So sigma of the sum of Si EI is equal to the sum of Si sigma of EI. Like where EI are the basis vectors of Rn. Right, so just to emphasize that we mean linear in the usual way. This gives us a subgroup of the chains in X, and if it's linear, then this restriction to each face is a linear map, and so this is a subcomplex. And if you cone, then directly from the definition, if sigma is a linear map, then this whole QP sigma is also a linear map. Right? So QP is going to take linear simplices and n plus 1. Okay, so given a point, we know how to form cones with that point as vertex. So if you want to subdivide, then the idea is, okay, you're going to pick some point to use for coning, right? So for example, this is where we're going. We're going to pick the barycenter here, and then we're going to take every face and cone it off with that as vertex, right? And that's going to give us our subdivision, right? So for that purpose, define the barycenter. So given sigma, let B sub sigma be sigma of the point with equal weight in every direction. This is called the barycenter. Bary, of course, coming from the word for weight. So it's just the center of weight. Okay, so define S from linear simplices, linear singular simplices to linear simplices inductively. So in degree 0, so if n is equal to 0, then S of a point is that same point. Right, so the subdivisions for a point is nothing, just a point. Right? And then for and then by S of a simplex is going to be Q B sigma of S of the boundary. Right? So if you know how to do it for simplices, for n simplices, then this is how you do it for n plus 1 simplices, because that's an n simplex, so you know how to do that, and then you cone. Right? So let's look at what's happening for small n. So if n is equal to 1, then we have our simplex looks like an interval, right? And it has vertices v0 and v1. The barycenter would be right there in the center. Okay, so S of the boundary, well, the boundary of sigma would be v1 minus v0. Right? S of the boundary, well, S is the identity on points. So S of the boundary would just be this again. v1 minus v0. And then you cone on that. Right? So QB sigma of S of boundary sigma would be B v1 minus B v0. Okay, so, and that's good, because we start out with an interval, and let's say it's going to the right, it's oriented towards the right, and we're dividing it into two subintervals, so we want them to both be going towards the right. Right? So that means that when you're doing BV1, then that's pointed the right way, so that should have a plus sign. Right? But when you do BV0, that's now pointing the wrong way. You listed the vertices in the wrong order, so that should have a minus sign. Right? So with that minus sign, then we really have this interval going to the right and this subinterval going to the right, which is what we want. Okay, if n is equal to 2. Okay, if n is equal to 2, then what you're doing is, well, you're going to do S of the boundary, right? OK, great. So every face gets divided in half. Then if you join the vertices with the those halves, that gives you the very center of the triangle, right? So we're going to end up with, let's say, V0, V1, V2. Let's say that this is B0, B1, B2, and then this is B3. So we're going to end up with all of these subtriangles, and they're each going to get a sign. And the signs are going to go like this. This is going to be minus, this is going to be plus, this is going to be minus, this is going to be plus, minus, and plus. Right? And the way they get listed are, well, you're going to cone twice, right? So that's going to add one of these vertices. So every time you cone, you put that vertex at the left. So the first guy is going to be B3, B0, V0. Right? And so why does it get a minus sign? Well, the large triangle is oriented with vertices 0, 1, 2, right? So let's, you can move this cyclically until the V0 is the first one, right? So this is the same as V0, B3, B0. And if you list them like that, then you're doing this one, then this one, then this one. So you're doing these in the wrong order, right? So that should have a minus sign when you compare it with the orientation of the large guy. Right? So let's put that in parentheses. And we could go ahead and list the other ones. So this guy would have B3, B0, B1. And then we would subtract this one, which would have B3, B1, V1, and so on.
With the first one having a minus sign.
Right, this one has a minus. Oh, thank you. Yeah, that's a minus, minus, plus, minus, and so on. Yeah. So this is equal to this. Well, let's say S of sigma. Okay, so that's our subdivision algorithm. You're going to keep splitting everything by its very center, and then that's going to give you a bunch of simplices of the same degree, but they come with signs. And here's something you can check, is that, maybe I was going to say that later. I'll go ahead and say it. The diameter of each subsimplex in S sigma is bounded above by the diameter of sigma times n over n plus 1. I think that's right. So the diameter of each of these small triangles compared to the diameter of the big triangle is, at most, since n is equal to 2, 2/3. Okay. So if you keep iterating this, you get 2/3 times 2/3 times 2/3 times 2/3, and that goes to 0. So eventually, you can get the diameter as small as you like. Okay. But an important thing to note is what happens when you hit it with the boundary. Okay, well, that's equal to the boundary of Q sigma S of the boundary of sigma. So we know what happens when you hit the boundary. So when you hit Q, you get the identity minus Q sigma of the boundary.
When you write Q sigma, is the
Q-
B implied?
Thank you. QB sigma is what I meant to write. Okay, so inductively, if S commutes with the boundary on Cn linear, then S commutes with the boundary on Cn plus 1 linear, because this term dies if S commutes with the boundary. Right, because you would get S of boundary squared sigma. Right. And and the induction starts with this is trivial if n is equal to 0, because S is just the identity. Okay, so T we also define inductively. Define T, so again, it's going to be on linear chains. So if you have a point, just take 0. And then after that, T of sigma is Q B sigma of sigma minus T of the boundary. Okay, so if sigma is an n-chain, boundary of sigma is an n minus 1 chain, T is inductively already defined and gives us an n-chain. So this difference is an n-chain, and then Q takes an n-chain and gives you an n plus 1 chain. Right, so it goes from and where it's supposed to. Okay, so let's check that boundary T plus T boundary is equal to identity minus S. Right. So again, by induction, right, this is clear if n is equal to 0, because both sides are 0. Right, so S is the identity, and both boundary and T give you 0. So if we know this for n chains, then on n plus 1 chains, let's do boundary T plus T boundary. Well, let's focus on boundary T. So boundary T would be just hit this with the boundary. So boundary of Q be sigma, sigma minus T, boundary sigma. We know what Q does with the boundary. So this would be the identity minus Q applied to the boundary. So boundary of sigma minus, well, let's see the boundary T boundary sigma. Okay, so that's sigma minus T boundary sigma minus, okay, QB sigma. And I want to, all right. I want to write this as, well, let's write out minus boundary T applied to boundary sigma. Okay, so now boundary sigma has degree n, yes, n, and so I know this formula holds already for n chains, right? So that boundary T at the end, I can replace it with what I get from over here, right? So, okay, I get sigma minus T boundary sigma minus QB sigma boundary sigma minus. Okay, so boundary T is equal to identity minus S minus T boundary. So identity minus S minus T boundary, all of that applied to boundary sigma. Right? So, okay. T boundary applied to boundary sigma, that dies because I get boundary squared. Boundary sigma minus identity applied to boundary sigma, those die. And so we're just left with plus S applied to boundary sigma. Okay, so we get sigma minus T boundary sigma minus QB sigma of S of boundary sigma. But of course, that is our inductive definition of S. So this is sigma minus T, well, let's write it like this, minus S of sigma minus T boundary sigma. Right? And so that's equal to T boundary sigma. So if you move this term over to the left, that's exactly what we wanted. Okay, so why are they natural, right? So if you have a map, so given a linear map, right, assuming both are convex subspaces of Euclidean spaces, then f sharp of S is equal to SF sharp, and f sharp T is equal to TF sharp. And this is because taking cones and barycenters are natural. Right, meaning specifically that if you do f sharp of q p of sigma, you get q f of p f sharp sigma. And if you do f of b sigma, that is the barycenter of f sharp sigma. Okay, and I've already mentioned that the diameter is goes to 0 as you iterate. So it also has the property that, so given any cover, of x, some iterate. So again, I want the interiors to cover x. Interiors. some iterate Sm sigma will be in will be in C U alpha n of x intersect C n linear of x for any sigma in C linear n of x. Note that m depends on sigma. Okay, so if we were only working with convex subsets of Rm, we'd be done. Here's what we do for an arbitrary space. Okay, so let Ln be an n-chain on, Ln is going to be a singular n-simplex of the n-simplex. It's just the identity. So define S from Cnx to Cnx by sigma goes to sigma sharp S of Ln. N, yes. Okay. So you do all of the subdivisions here. So you think of delta n as a topological space itself. It is a convex subset of Rn. So you can do all of the things we've been doing there. So you just do that, and then you view sigma as a map from delta n to x, and so it allows you to push forward chains along it. So just take the induced map on chains and do that.
How are you defining S in terms of S?
So this is the S on delta n, and this is the S on x. Right? So on delta n, we have definitions because it is a convex subset of Rn.
Okay.
Right? Right, so this works because L sub n is a linear n-chain on delta n. So similarly, T from Cnx to Cn plus 1 x just takes a chain to the push forward under sigma of T of Ln, right? Where this is the T on delta n, and we get a T on x. Okay. So I'll just say it's easy to see that these satisfy the desired properties. Okay, so they satisfy the desired properties on convex subsets of Rn, and then you're just pushing them forward, so I'll let you check that they still satisfy those properties, but now for an arbitrary topological space. Okay. Wonderful, so that gives us the proposition. Remember, the proposition said that if you pick a basis, then the homology you get by restricting singular simplices to those whose image lies inside the the interiors of the cover, that homology is the same as singular homology. Okay, so let's use that to prove excision theorem. Excision. Right, remember excision says that if you have C inside A inside X with the closure of C contained in the interior of A, then the homology of X relative to A is the same as the homology of X minus C, A minus C for all n. Right? And to be more precise, not only are they isomorphic, but the inclusion of the relative chains from here into the relative chains here induces an isomorphism. Okay, so the proof is, let's apply the proposition with the cover A and X minus Z. Right? So by this assumption, the interiors cover X. Right? Okay, so at the level of chains, we have the following. The chains in X minus Z map into the chains that are correspond to this cover, which then map to the quotient by CNA. Right. So we can run the same proof that we had at the end of last class. This composition surjects, and its null space is precisely the chains in A minus Z. So we get an isomorphism of chains chain spaces like that. And then when we pass to homology, we get, so here, it's easy to see because this is, it's easy to see that you get the isomorphism from the proposition also works for relative homology groups. And you don't even have to reprove the proposition. You can just use the long exact sequence of a pair corresponding to the cover and conclude that you have the isomorphism. But in any case, this is going to be U alpha n of x comma a. And what we've proven is that this is Hn UL without the U alpha of x comma a. Right? And the map is just the inclusion here. Right? So this is induced by the inclusion. So it essentially is the same proof we gave in the delta complex setting. It's just we had to work pretty hard to see that this actually gave us the same homology. Okay, excellent. So we have excision. Okay, and we have perfect. So here's an easy payoff from excision. we initially computed using the long exact sequence of a good pair, and now we can prove that that exact sequence it works. So here's a corollary. If XA is a good pair, right? Remember that means that A has a neighborhood in X, so U open and deformation retracts to A. Then the relative homology groups are isomorphic to the relative homology groups of the quotient space. And the isomorphism is induced by the quotient map. Right, so of course, you have to apply the quotient map to the pair, so that's okay. We have a map of pairs that takes this to X mod A and A mod A. Okay. Okay, so since U comma A is homotopic, let's say, to A comma A, the homology groups of UA are all equal to 0. Right, so we saw last time that the relative homology of a space relative to itself is just always 0. So these groups are always 0. Okay, so from the long exact sequence of the triple, XUA, well, since these are all going to be 0, that means that the other ones in here are going to be isomorphisms, right? So, so remember what this would be is XU maps to UA maps to XA maps back to XU. So this would be n plus 1, this would be n, and then n minus 1. UA. So if this is 0 and this is 0, then this map is always an isomorphism. Right? So in this diagram, we have Hn of Xa. That maps to Hn of Xv. There's no V, there's U. And on the other hand, we can map there from Hn X mod A, U mod A. Or we can take the quotient, and then we would be in X mod A mod A, X mod A, U mod A. Oh, sorry. This should have said X minus A, U minus A. And then here I want X over A minus A over A, U over A minus A over A. So we saw that this is an isomorphism from here. This is an isomorphism by the same reasoning. These two are isomorphisms by excision. Okay, and this is an isomorphism. So the right most vertical arrow is an isomorphism because Q is a homeomorphism away from A. Now, Q doesn't do anything to points that are not in A. Okay, so as this diagram commutes, the leftmost arrow is an isomorphism. Okay, so the fact that the diagram commutes is easy to see in this case. We'll see a much more general statement that passing from short exact sequences to long exact sequences to homology is natural. What natural means there is that if you have a map of short exact sequences, it induces a map of long exact sequences. Right? And maps of sequences mean commuting maps, commuting diagrams. Right? So we'll see that soon. But in any case, in this case, they commute. And so perfect. So then if you want to go know that this is isomorphic to this, you just go around. Right? And you get an isomorphism. Okay, perfect. So that justifies our computations of the homology of spheres, for example. And we're just out of time, so good place to stop.